If you release an object, it's going to get pulled towards the ground. Yeah, no kidding. I figured that out when I was like a baby. Okay, good. What causes that? Easy, gravity. All right, well, how does gravity work? Well, the Earth is a really big mass, and really big mass means it has a lot of gravity. So you have a tennis ball and it comes near to a big mass, it knows to get attracted or pulled by gravity. Kinda, but let me ask you this. How does the tennis ball know that there's a big Earth there and that it's supposed to fall towards it? I mean, if we were in space and I held the tennis ball and I let it go, it would just float there, not attracted to anything. But now that I'm on the surface of Earth, the tennis ball doesn't have any eyes. How does it know that it's close to a large object and it knows that it's supposed to fall towards the ground? What tells it that it's supposed to fall due to gravity? Well, when the ball, it comes close and it, I don't know, but it does. It knows and it falls down. That's what happens. Gravity could probably be classified as one of the most commonly known forces, but the one that we actually know the least about how it actually works. Because, that's a good question. How does this know that there's an Earth there and it's supposed to fall towards the ground? How does it know that it's supposed to fall due to gravity? Well, we see kind of similar phenomenon with magnets. When I move this magnet here, we can see that the other one moves in response to it. And it doesn't have eyes either to look and see the other magnet, but we describe this as being in a magnetic field. And we can draw these field lines to show the direction that a north magnet would feel a force in this magnetic field. And that's how we describe gravity as well, that this tennis ball and me and everything on the surface of Earth is in a gravitational field. It's one that's invisible, we can't see it, but we know it's here because when we drop things, they act in response to this field. The true nature of gravitational fields, what they look like and what brings them about, is actually still kind of being researched and learned about even to this day. However, in this lesson, we'll take a look at how Newton's laws accurately describe how gravitational fields work and how objects operate in them. So let's take a look at gravitational fields. Okay, so let's start with looking at the tennis ball and looking at the Earth, and we can see this drawing of the gravitational field. What I've drawn here to show the gravitational field are called field lines. These are lines that whenever you place an object there that's subject to the field, it would follow those lines. So if I place something here, it's going to go towards the Earth in this direction. If I place something over here, it's going to go towards the Earth in that direction, or it's going to feel a force in that direction. Now we'll look at calculating how much force it's going to feel in the next lesson, but right now we're just going to look at the nature of the field. So look where the tennis ball is. This one's pretty far away from the Earth's surface, but we're going to consider not the tennis ball, we're just going to consider what the field is like at the location. So we're not worried about the tennis ball itself, we're saying how strong or what is the field at that location. Okay, well, what makes the field is this big mass called the Earth. The mass is going to be the thing that causes the gravitational field. So I'm going to put it with a label here, MS. That means mass source, the source of the gravitational field we're looking at. The tennis ball has a gravitational field as well, much, much weaker, but we're not worried about its right now. We're looking at the Earth's gravitational field. Okay, what else is important is how far you are away from this mass. And we can actually see with the lines an indication of how strong it is. So field lines, when they're close together, it means it's a stronger field. So you can see here, if I draw a ring around, these lines are all quite close to each other. But as I spread out and I go all the way up here, we can see the lines are further apart. And that shows that as I get further away from the mass, or from the Earth, that the field strength is going to weaken. You can kind of see all the way above me here, the lines are quite far apart here. That's showing a weaker field much further away from the Earth. So how we're going to consider that number is along that circle. If I was going to keep drawing here, anything at this distance should have the same field strength because it's all the same distance from the center, which we're going to call the radius, how far it is away. So the distance from the center of the Earth is going to be called our radius here, distance from the mass source. Let's put that with an R. So how are these two variables going to affect our field? Well, as the mass goes up, the field strength is going to go up, stronger gravity. If the radius goes up, it's going to get weaker. We're going to have weaker gravitational field. So let's put this into G. This is our gravitational field. is equal to, well, mass on the top and radius on the bottom. As mass goes up, gravity is going to go up, or our field, or gravitational field goes up. The radius goes up, well, that's going to cause the gravitational field to go down. And that's a basic relationship between mass and radius, but we have to throw a couple other things in here. It turns out as we get further away from the mass source, the gravitational field doesn't just go down linearly, it goes down exponentially. So what that means is we have to throw a squared in there here, r squared, that if I increase the radius a bit, I square that number, and that's the factor that the gravitational field strength is going to go down. It's sometimes written as the field will decrease with a square of the distance, which sounds complicated, but it just means it's r squared. Okay, the other thing is when we're calculating the number for g, the gravitational field strength, it actually ends up not being this number. We had to kind of just plug another number in there to make it match what we actually see in real life, and we're going to call that the gravitational constant. It's shown with a capital G, and it's the same number every time. It's a big number. Well, I should say it's a big number to write, but it's actually a very small number. 6.67 times 10 to the negative 11. When we throw that in there, it makes this g match more of the values that we see in real life. So that's the equation for gravitational field strength. Let's take a look at using it for some problems. So our first problem is going to be, what is the gravitational field strength on the surface of Earth? Okay, so here we got Earth, and we're looking for the gravitational field strength right here on the surface where we spend most of our time on the surface of Earth. What is the nature of the field? What's the strength of the field at this point? Well, let's put up our equation. G, gravitational field strength, is equal to capital G, that's our constant, ms over r squared. Start plugging in some numbers. No rearrangement here. Start plugging in some numbers. So I'm going to start with that constant. Once again, 6.67 times 10 to the negative 11. It's always that number for the gravitational constant. Next, I need to look at mass source. And why I'm going to emphasize source here is if it maybe says, there's a satellite orbiting somewhere, or we drop a ball on the surface, you're not worried about that mass. You're worried about the source of the gravitational field when we're asking for the strength of it. So that is going to be the Earth. The Earth is creating this gravitational field. We plug in the mass of the Earth. Now, usually there's a data sheet in your grade 11 class, your physics class, that tells you that constant. So probably don't have to memorize that. You can probably look it up. It's about 5.97 times 10 to the 24 kilograms. It's a really big mass. Really big mass, and you can kind of see this isn't necessarily that hard to plug into, but I think the hardest part for these questions is putting it all in your calculator and keeping track of these numbers. So make sure we enter that carefully. And last, we have to divide by the radius. Now, that's the distance from the mass source. And sometimes students think, well, it's right on the surface. Isn't the distance 0? That's a good thought, but we're going to measure to the center of the mass source. We're going to measure right here to the center of the Earth. So from the surface to the center, maybe see this better with red, the surface to the center there, that's going to be the distance we're looking for. We're going to call that the radius. Okay, how far we are from the center of mass that is creating this gravitational field. So that radius is called the equatorial radius of a planet. And once again, it's usually on a data sheet that you can look up in your class. And we look up the equatorial radius of Earth, and we get 6.37 times 10 to the 6 meters. Okay, 6.37 times 10 to the 6 meters. Now, if we plug those values in correctly, we should get a number of 9.81 for our answer. And hopefully 9.81 is familiar because we described this before as the acceleration of gravity when you drop anything on its surface. And that kind of gets the idea as well. I'm not worried about the object I'm dropping. I'm just looking for what's the strength of the field there. And that turns out to be the acceleration of gravity is described by its field strength. You can describe it with 2 units. You can either be newtons per kilogram, meaning it will pull with 9.81 newtons for every 1 kilogram, or what it's going to cause it to accelerate at 9.81 meters per second squared. So I like this example because it describes the field strength as what objects will accelerate there at, and it shows how we get that 9.81 answer and that the formula works. Let's try one more example in maybe a less familiar place. We're going to go out to Mars. So this question says, if a satellite is designed to orbit Mars, where the gravitational field strength is 0.75 newtons per kilogram, how high above the surface does it need to be? Okay, so we have our satellite that's going around Mars, and it's looking for field strength of 0.75, which is much lower than 9.81. because it's a smaller mass. Mars isn't as heavy, and the satellite's going to be further away from it than when we're looking at on the surface of Earth. So that's going to make for a pretty small field strength. Let's figure out how high above the surface it has to be. Now, since it gave me information about a gravitational field, I'm going to start with that formula for gravitational field. What are we solving for? Well, we know the gravitational field. Capital G is a constant, and I know the mass source from, again, your data sheet. So what I'm trying to find information about is actually the radius, the distance to the satellite. So let's do a rearrangement there. There's the R labeled on Mars there. Let's multiply R up here, so it would be R squared times G. Looks a bit messy, but we'll divide G over to the other side, and we're looking close to the correct formula of what we need. Last, we'll just get rid of that square and square root the other side, and we're able to solve for that radius. Let's plug in our numbers. So we have G, the constant, again for Earth, Mars, Saturn, doesn't matter. Gravitational constant, always 6.67 times 10 to the negative 11. Now I'm going to throw in the mass of Mars. It's a little bit different on your data sheet, a little bit lighter, 6.39 times 10 to the 23 kilograms. Lastly, put in the field strength that was given to me in the question, 0.75 newtons per kilogram. Make sure we plug that all in correctly, and we get an answer of 7.538 times 10 to the 6 meters. And often you'll look on an assignment or look on a test, and that'll be an option, maybe that's C, and you circle it. You get the question wrong. Why do you get the question wrong? You had this exactly correctly rearranged, you plugged in the right numbers, and you got an answer for radius. The question did not ask for the radius. It asked for how high above the surface. And you can see in our picture, from here to here, that's to the center of the planet. That's not the height above the surface. So we need one more step to get to the height above the surface. So what are we looking for? We're actually looking for this section here in pink, and we need to subtract this part here in blue. How could I find that part in blue? Remember, this is from the surface to the center of the planet, and that's on your data sheet as the equatorial radius. So if I take my green number here, minus the blue number, I should be left with the pink, the height above the surface. So we look up on our data sheet, and the equatorial radius of Mars is 3.39 times 10 to the 6 meters. So I subtract that, and I get a number of 4.1 times 10 to the 6 meters for our height above the surface. Not sure why I have a negative there. It should be positive, but 4.1 times 10 to the 6 meters for the height above the surface. So things that trick people up there, which radius is which? I'm subtracting the equatorial radius. You might see orbital radius on a data sheet as well. That's how far Mars would orbit from the sun. So you're subtracting its equatorial radius to solve for the height above the surface. Okay, so I hope that helped you with doing some calculations for gravitational fields. If you did find that useful, we do have an entire course playlist. You can check that out on the channel. Thank you so much for watching, and I will see you in the next video.